Hello everyone, welcome back to lesson number 21 for BC Calculus. Today we are talking about theorems. In the last video we talked about Rolle's theorem and the mean value theorem, and I showed you guys the criteria that you needed in order to apply Rolle's theorem and mean value theorem. And then we did a pretty straightforward mean value theorem question, and then the Rolle's theorem problem that we did, we were not able to apply it because it did not meet the particular criteria that we need for it to happen. Well, I chose a really basic example where you will apply Rolle's theorem, and I'll just show you guys the simplicity of that theorem based on this really simple example here. So we have the function x squared minus 2, and or on the interval from -3 to 3. And so the first thing we have to ask ourselves in order for Rolle's theorem to apply is the function continuous over the function of -3 to 3? And the answer is yes, right? We know that this is a polynomial, we know it's a quadratic, and we know it looks something like this, right? This is what the function looks like. So not only do we know that it's continuous on the interval from -3 to 3, it's continuous everywhere. Well, I can also say the same thing about differentiability. It's differentiable everywhere. So I know those two things. We were not able to get to the next part of this because this was actually not true in the previous video. So the third and final thing you have to show before we actually apply Rolle's theorem is our f of a equal to our f of b. So if I plug in -3 to my function, I'm going to get -3 squared, which is going to be 9, minus 2, which is 7. And if I plug in 3 to my function, I also get 9 minus 2, which is equal to 7. So I can also say this is true. So here's the three criteria that hold true for this function. So now I can apply Rolle's theorem. And Rolle's theorem is actually very simple. You're going to find the derivative of the function, which in this case is going to be 2x, and we're going to set that derivative equal to 0. You're going to set the derivative equal to 0 because Rolle's theorem says that on the interval from -3 to 3, like on the interval from -3 to 3, and we go around this curve, there's going to be at least one value c where the derivative is equal to 0. Well, if we set this equal to 0, we get it x equals 0. So in this value right here, x equals 0, we get a horizontal tangent of y equals 0, or the slope being 0. So our derivative is 0 at this value. So the c value, if you want to, is the same thing really as the x value. So when c is equal to 0, then we are going to get a derivative of 0. Okay, that's all Rolle's theorem is saying. Is continuous, yes. Differentiable, yes. If f of a equals f of b, yes. Find the derivative and simply set it equal to 0. And then figure out what value gives you that. And that's the answer for Rolle's theorem. So it's just that simple, ladies and gentlemen. So now let's go ahead and do some other questions. So sometimes it may not be blatantly obvious that you need to use one of these theorems. So for example, number 4, it says, suppose that f of 0 is equal to -4, and that f prime of x, this whole derivative will always be less than or equal to 5 for all values of x. How large can f of 2 possibly be? So we can look at this and say, well, this is going to be the instantaneous rate of change at some value x, and that we could say, all right, well, let's look at, and this is going to be a mean value theorem example, because if I ask you to look at the interval from 0 to 2, right, then I can find the average rate of change. The average rate of change would be f of 2 minus f of 0 all over 2 minus 0. And in order for mean value theorem to apply, this has to be, now remember we want it to be set equal to 5, but this is saying that the derivative is going to be less than or equal to 5. So I know that this has to also be less than or equal to our 5. So this is all we have to do. We plug in f of 0, which is going to be -4. And we're going to get that this is, and we're going to cross multiply, we're going to get 10. And then minus a negative is plus a plus. So I get f of 2 plus 4 must be less than or equal to 10. And so f of 2 must be less than or equal to 6. So the highest that f of 2 can be is actually 6. So this is just a little hybrid of looking at the average rate of change and the instantaneous rate of change. Okay, so that is, again, a mean value theorem question. Go ahead and stick with mean value theorem for another time here. We're looking at driving on Interstate 95. from Springfield, Virginia to Savannah, Georgia. And he is visiting his grandmother for her birthday at time equals 2. So at f of 2, we're looking at 110. All right, he's at mile marker 110. At f of 5, he's at mile marker 290. And so assuming that the posted speed limit is 55 miles per hour, is there enough evidence to prove that Imran was guilty of speeding during this trip? So let's look at it. Well, let's find the average rate of change of our function first. And we do this. And so we get 290 minus 110 all over 3, which gives us 180 over 3, which is 60. So this is saying that he was averaging 60 miles per hour over the course of our 2 p.m. to 5 p.m. So if the average was 60 miles per hour, not only was he speeding, he was speeding for the majority of the trip. So then, yes, we could say that there is enough evidence for this, that the average rate of change was 60 miles per hour by the mean value theorem. So again, if the average rate of change is 60 miles per hour, he had to go over 55 at least one moment in time, which again, if the average is 60, then he went over quite a bit. So that's just an example of the mean value theorem. So let's go look at some more Rolle's theorem questions. So example number 7 says, let f be a polynomial function. So again, polynomial, that word polynomial means that yes, we're continuous and we are differentiable. So we automatically know that those two things are true. With a degree greater than 2, okay, a is not equal to b, and we know that f of a equals f of b, and that equals 1. So this right here is just screaming Rolle's theorem. And I know I can apply Rolle's theorem because, again, the function is continuous and differential because it tells me that it's a polynomial and that f of a must be equal to f of b. So I know a, b, and I know that they're both equal to 1. Right, so they both equal to 1. So this says, which of the following must be true for at least one value of x between a and b? So the first thing says that I have to cross the x-axis, that I have to have a 0 on the interval from a to b. And so that's clearly not true. That's clearly not true because, I could draw a line straight across. I can come down really close to it and then come right up. I can come up and down like this, a lot of stuff. I do not have to cross the actual axis here. So I'm going to go ahead and just draw myself a little curve. So there's our counterexample for this one. So again, blah. It says that f prime of x, so some value of x has to be equal to 0. So this is absolutely true. And this is true because of Rolle's theorem. That's what Rolle's theorem is saying. And so for this particular example, we are looking at where is this happening. And so let's actually rewrite this just for a second as a c. And so that's what this says. That there had to be some value on this interval from a to b where my derivative is equal to 0. I have to have a horizontal tangent somewhere on this curve, and that's exactly what you see right here. And so we know that at least 2 is correct. So that gets us rid of b, and that gets rid of a. So we have 2, d, and we know that, well, and the funny thing is here, we already know that 1 is not true, so this is a silly one. So I wish this had said 2 and 3, so we can talk about why this one's false. So why is this one false? So this says the second derivative must be equal to 0. Well, second derivative is concavity. So in order for my second derivative to be 0, I have to have somewhat of a change in my concavity. Well, the graph I actually gave you here is actually always concave down. So my second derivative for this particular example is always going to be less than 0. I don't have a point of inflection, which would be what I need here. So this is also not correct. So without doing too much thinking, the answer here is just C. And again, this is just an extension of Rolle's theorem. It's the extension of Rolle's theorem. And we haven't talked about this one in a minute, but let's go ahead and talk about our good old friend IVT. This is a refresher on this one. It says let f be a function that is differentiable. So again, if it's differentiable, ladies and gentlemen, we automatically know it's continuous. So if it's differentiable, then we can automatically say it's continuous on the open interval from 1 to 10, which means that it's continuous on the closed interval of 1 to 10. Okay, so now that it's continuous and differentiable, we can now start graphing this thing. And so I'm going to go ahead and open up my little page here for this. So We're going to graph it and just kind of look at the idea. And like, sometimes it's just, how did I know it was IVT? Well, I've done the problem before, so that's probably why I know it is. But sometimes just graph it and just see, what it's actually asking for. So f of 2 is equal to -5, and then it tells me at f of 5, I'm up here at +5, and then at f of 9, I'm back down here at -5. And so I know that this, again, is a continuous function, and it's also differentiable. So I know that from 1, again, I don't know what's going on with this, but at least I know this graph looks something like this, right? I've got to be able to connect these points because it's a continuous function. So f has at least 2 zeros. Well, that's absolutely true. There's a 0 here, and there's a 0 here. And that's why IVT works. So we start out at x equals 2. We're at a -5. And then we go to f equals 5. We're at a +5. So our function traveled from a negative value to a positive value. So that's exactly what IVT tells us. IVT simply says that if I go on the interval from 2 to 5, if I'm at -5 and I pop at 5, there's going to be some value of c. Now, I don't know what this value is, but I know there's some value of c that my derivative is actually equal to 0. So that's what IVT is telling us, is that f prime of c has to be equal somewhere on the interval from 2 to 5. Because again, the function is continuous, and that's exactly what you see here. So here and here. The graph of f has at least one horizontal tangent. One horizontal tangent. So let's look at that. Well, the way we graph this, we have to come all the way up, and then eventually we have to come all the way back down, right? We have to come back down here. So it may not have happened here. I could have had the graph continue going up, but eventually it does have to come back down. So we know there's at least one horizontal tangent right, again, somewhere up here. So I could have drawn the graph again, ladies and gentlemen, where I could have went up and then down to right here, and then it would be right here. But at least I know there's at least one horizontal tangent. All right, I'm going to get rid of that craziness of that graph that I showed you. But yes, so the answer to that one is also true. So now this is true. And then it says for some value of c on the interval from 2 to 5, so on this interval here, from 2 to 5, there's got to be some y value that's going to be equal to 3. And so y equals 3 is right here. And so what that means, ladies and gentlemen, is that if I look at the line y equals 3, on the interval from 2 to 5, the function has to cross the function has to cross this line on that interval, and it does. It crosses right there. And that's also by IVT. This is also by IVT. So this is also true. So this example, all three of them are true. So I hope that makes sense with you guys as well. Those are just extra practice examples. We are going to come back and do a couple more practice examples for IVT, mean value theorem. I got a really good example I want to show you guys, and then we're going to learn the average value theorem. So I'll see you guys in the next video.